Hello, my name is Martin Beisel, and in this video I'll present our paper, Pattern-Based Generation and Adaptation of Quantum Workflows. In the first step of our approach, the user can select from a variety of algorithm patterns used to solve different problems. Additionally, they can use so-called enhancement and behavior patterns to customize the selected algorithm for their use case. In the second step, the quantum workflow is generated based on the selected algorithm patterns. Thereby, a solution repository is searched for suitable implementations of the respective patterns. Algorithm implementations are commonly available as monolithic scripts. To also enable integration of these kind of implementations in a scalable and customizable manner, we use a script splitter that can split script-based quantum applications into the individual building blocks. In the third step of our approach, the selected behavioral and enhancement patterns are integrated into the quantum workflow. Subsequently, users can adapt the workflow and add or remove enhancement and behavioral patterns. In the quantum algorithm enhancement phase, the enhancement patterns added to the workflow are replaced by suitable tasks implementing the pattern's functionality. Thereby, modeling constructs from the quantum modeling extension QuantMe are utilized. QuantMe provides custom-tailored modeling constructs for building and configuring quantum applications. After all enhancement patterns have been applied, the behavioral patterns are processed to change the semantics of the algorithm execution. For example, the workflow is rewritten for executing it in a so-called hybrid runtime that reduces latency for alternating classical and quantum executions. Next, in the workflow transformation step, all QuantMe modeling constructs are transformed into native workflow modeling constructs of the used workflow language. Since packaging applications is crucial to share, distribute, and sell them, in the 8th step, all required software artifacts of the quantum workflow are bundled into a self-contained quantum application archive. In the last step of our approach, the previously packaged artifacts are deployed in the execution environment of the workflow. Then the workflow can be executed and monitored. To realize our approach, we designed a system architecture comprising 6 core components. Pattern Atlas is a tool for authoring and managing patterns, pattern languages, and the corresponding solution implementations. The QuantMe framework enables modeling workflows using BPMN and the QuantMe modeling extension. It was extended to also support a pattern-based modeling of quantum workflows. The script splitter is used to split script-based quantum applications into the individual building blocks. Binary and OpenTosca are used to model and deploy all required services. The workflow engine is utilized to execute the modeled quantum workflows. To showcase the practical feasibility of our approach, we implemented a prototype realizing our system architecture and used it to implement 3 different use cases from the quantum domain. In this video, I'll showcase the use case solving the maximum cut problem employing the quantum approximate optimization algorithm, short QAOA. QAOA is a variation of a quantum algorithm that utilizes parameterized circuits. To find good parameters, a classical optimizer is used, which aims to iteratively improve the result quality by adjusting the parameter values for each execution of the circuit. To start off with the pattern-based generation of a quantum workflow, we click on Pattern. Then we open the pattern selection. We click on Select Patterns, then on the plus. And here we select the QAOA algorithm. And then we also add circuit cutting, a warm start using a biased initial state, and readout error mitigation for our algorithm. We click on Confirm. Then here we could add another algorithm, but for this use case we just require one algorithm. We click on plus, and done. Then we click on Combine Solutions. And we now here have our quantum algorithm with the patterns attached to it. Now we do a pattern transformation to add the patterns to our workflow. Before we click on Transform, and this take a second. And as you can see, here our warm starting, circuit cutting, as well as the error mitigation have been added to the process. As you can see, the workflow now contains various QuantMe modeling constructs, and we now need to transform it into a native workflow. Hence, we enabled a QuantMe transformation. Click on Transform once again. And now our workflow only contains service tasks which implement the patterns as well as the quantum algorithm. As you can see, some of the services require deployment. So we now click on OpenTosca and service deployment. Then we see the tasks that require deployment. We click on upload CSARs to upload the deployment models. In this use case, we already pre-deployed our services, so we can immediately bind the running services to the tasks. Since all tasks can be executed now, we can deploy the workflow. Hence, we click on Deploy Workflow. After deploying the workflow, we can now execute it. Thus, we click on Start Process, select our process, then enter our IBM Q token, and select the noise model that we want to use for a simulator. Then we click on Start Process. Then we can go to the Commander cockpit to observe our execution. Select our process, and as you can see, we are now in the parameter optimization. If we now refresh, we see that we are already in the third execution. And if we want to observe the workflow in more detail, we can switch to the quantum view, which shows the original form of the process. And as you can see, we now here have our quantum tasks again, and we can now hover over them to get some more details. For example, we can have a look at the circuit or the evaluation, or interestingly, we can also analyze the optimization history. We can see after 2 iterations, not much happened yet. But if we reload now, we see that our optimizer is like looking for better parameters. After a couple iterations, we can reload again and see that our optimizer is continuously finding better parameter and is exploring the optimization landscape. After reloading now, we can see that our process finished as our token is in the Analyze Results task. So we can now check again optimization history and see that we found the best value at around 15 iterations. By hovering over the Evaluate Results, we can see what the algorithm determined as the optimal maximum cut.